In the last video, we graphed a polynomial, so we kind of knew what to expect from its graph. This one, we've got no idea without technology what this is going to look like. So we're really going to have to rely on our derivative information to come up with the graph. All right, so I've got f of x equals 3 times x to the 2/3 power minus x. Let's start off with our intervals of increasing and decreasing. So let's find the derivative of f. So I'm going to let that 3 go along for the ride. Power rule on x to the 2/3, bring down the 2/3. X to the 2/3 minus 1 is going to be negative 1/3. And then derivative of negative x is negative 1. So let's simplify this a little bit. I've got the 3's that can cancel out. I'm also going to move that x to the negative 1/3 down to the denominator. So let's see, I've got 2 that's going to stay up top, x to the 1/3 on bottom, and minus 1. Also, to make this one a little easier to think of when we're finding critical points, let's change that x to the 1/3 into a cube root of x. Remember that critical points happen when the derivative is equal to 0 or is undefined. This one's actually going to have one of each of those kinds of critical points. The undefined point is pretty easy to see. If I look at that derivative, I see if I try to plug in x equals 0, I'm going to cause division by 0, and I can't do that. So x equals 0 is our first critical point. And this one actually also is equal to 0. So let's see when that happens. We're going to solve for x. So I'm going to add 1 to both sides. And I get 2 over the cube root of x is equal to 1. I'm going to multiply both sides by the cube root of x to clear out the fractions. And I have just 2 left on the left-hand side, equals 1 times the cube root of x. And we'll just cube both sides to get rid of the cube root. And I get 8 equals x. So my next critical point is at x equals 8. All right, so let's fill in our sign chart and figure out the increasing and decreasing. All right, so we're going to pick any point to the left of 0. I'm going to find f prime of, let's say, negative 1. I'm going to find f prime of 1. That would be between 0 and 8. And then something to the right of 8. I'm going to look ahead to my derivative. I'm about to plug in some numbers there. I'm going to take the cube root of x. So I'm going to put 27 here. That's the next perfect cube after 8. That'll make it easier to plug in. It really doesn't matter, especially if you're relying on a calculator. You can put whatever you want in there as long as it's bigger than 8. All right, so I'm going to find f prime of negative 1, f prime of 1, and f prime of 27. All right, so I got something negative in the first region, something positive in the middle region, and something negative in the third region. All right, so let's change that into increasing and decreasing information. So this means that f of x is decreasing on this interval, increasing here, decreasing here. So let's write that information down, and then we'll go store it on our final answer graph paper. We've got f of x is decreasing on negative infinity up till 0, and then from 8 to infinity, and then increasing on the middle interval from 0 to 8. All right, let's go store this information on our final answer graph. All right, here's my final answer graph paper. We're going to store our increasing and decreasing information. We want to note that our critical points are at x equals 0, that's on the y-axis, and x equals 8. So let's go make enough tick marks to get over to 1, 2, 3, 4, 5, 6, 7, 8. And I'm going to draw those vertical lines again that are going to split up my graph that I'll end up deleting at the end. All right, and then we'll just take a note that we are decreasing up until we get to 0. And we are increasing in between. And then decreasing after 8. All right, let's go find our local minimums and maximums. All right, so we know we went from decreasing to increasing at x equals 0. So we're going to have a local min at x equals 0. So we'll go ahead and find that y coordinate, our function back up there, f of x. Let's find f of 0. 3 times 0 to the 2/3 minus 0. It's a bunch of zeros. So this is going to be at y equals 0. And then we know we're increasing up until we get to 8 and then decreasing thereafter. So we're going to have a local maximum at x equals 8. So we have a local max at x equals 8. All right, so let's find f of 8. F of 8 is going to be 3 times 8 to the 2/3 minus 8. 8 to the 2/3, you could do that on a calculator, or let's just remember that that's the cube root of 8 squared. So this is 3 times the cube root of 8 squared. All right, so 8 squared is 64. Cube root of 64 is 4. So we've got 3 times 4, that's 12, minus 8 is equal to 4. So we've got a local maximum at 8, 4. Let's go mark those 2 points on our graph. All right, so our local min is happening at 0, 0. Remember, the y-axis is currently underneath my green line, so I'm going to put my point 0, 0 there. And then I'm also going to put in the local max at 8, 4. So this will give ourselves 8, 1, 2, 3, 4. So we'll come over here and have our local max right there. I'm going to notate one more thing here before we go on to the second derivative and concavity. Remember the way that we found those two critical points. X equals 0 we found by looking at where the derivative was undefined. X equals 8 we found the derivative was equal to 0. So I'm going to make a note of that because that's going to change what the graph looks like. So we found that f prime of 0 did not exist. It was undefined. But f prime of 8 we got by solving the derivative equal to 0. Now, the reason that makes a difference is because where the derivative doesn't exist, remember what that looks like. That's either a corner, a cusp, or a vertical tangent. So we're going to have to keep in mind, we're going to have to use one of those when we come up with the graph of f of x. All right, let's find the second derivative and do our concavity information. So we're going to find f double prime of x. The 2 is going to go along for the ride. We'll bring the negative 1/3 down. And we're going to subtract 1 from the negative 1/3. So always we can come off to the side and do our little scratch work. So negative 1/3 minus 3/3, and we get negative 4/3. So that's our new exponent and our derivative, negative 4/3. And then the derivative of negative 1 is going to be 0. All right, so let's simplify our second derivative a little bit. I've got that x to the negative 4/3. I'm going to bring that down into the denominator with a 3. So I'm going to have 3x to the 4/3. And then what's left up top is the 2 and the negative 1. So we'll write this as negative 2. And then just for ease of thinking about it, let's transfer that 4/3 into a radical. So I'm going to have negative 2 divided by 3. That's going to be the cube root of x to the 4th. You could simplify that a little bit more, but this is going to be good enough for us. This one is never going to be equal to 0. It's a standalone fraction. Negative 2 is never going to equal 0, but it will be undefined when x is equal to 0. When we plug in x equals 0, we get division by 0. So only one possible inflection point. I'm going to put a 0 on here and test the second derivative. So f double prime of x, let's plug in a negative value and a positive value. So we're going to come find f double prime of negative 1 and f double prime of 1. All right, so let's take our second derivative and plug it in. So negative 1 to the positive 4th is a positive 1. Cube root of positive 1 is positive 1. So we're going to get negative 2 over 3. Let's plug in x equals 1. Again, 1 to the 4th is 1. Cube root of 1 is 1. 3 times 1 is 3. So we get another negative 2/3. All right, so here we have a negative thing and a negative thing. So this function is actually always concave down. All right, so we're going to say that f of x is concave down like a frown, concave down like a frown. Okay, so f of x is always concave down. That actually means that we don't have an inflection point. In order for that x equals 0 to count as an inflection point, we'd actually have to change concavity. So we're just going to say that we're concave down always. All right, so all I've got to add right now is that f of x is always concave down. So I'm just going to say across the board, we are always concave down. All right, so everything we draw is going to be concave down. All right, so I'm actually not feeling terribly comfortable about how to draw this graph, particularly before I get to x equals 0. I don't have any points plotted over there because we didn't find any maximums or minimums over there. And so I'm just going to plot an extra point. Let's graph x equals -1. So I'm going to plug that into my function. So I'm going to come up here and say f of -1 would be 3 -1 to the 2/3 minus a -1. And we can just rely on the calculator to tell us what this is. And I get y equal to 4 here at -1. All right, so I'm going to go ahead and plot that point, -1, comma 4. So I think I have enough to go off of here. So I'm going to start off over on the left. I know I'm going to be decreasing. So I've got to start above that y coordinate of 4 that I'm going to come down towards. And I have to decrease in a concave down way. So I'm going to start up somewhere above y equals 4, decrease in a concave down kind of way. I'm going to decrease in a concave down kind of way and head down towards my point at 0, 0. So when I get to 0, 0, that was my local minimum. So I know that I'm going to have to start increasing. That's my local minimum. Remember, though, that f prime of 0 did not exist. So we said we were going to either have to have a cusp there or a vertical tangent. So I'm thinking if I have to start increasing now, that the cusp seems a bit more likely. So I'm going to draw this with a cusp at x equals 0, and I'm going to start increasing, but I have to increase in a concave down kind of way. So I'm going to increase in a concave down kind of way until I get to x equals 8. And then I'm going to have to start decreasing in a concave down kind of way. So we're going to treat that like our local maximum, and we'll start to decrease. All right, so I'm going to put some arrows on my function, and hopefully this looks good. And you can go type this one in on Desmos and see what it gives you.